Good afternoon, everyone. My name is Zhuo, and I'm assistant professor from Xi'an Jiaotong Liverpool University. Today, I'll present a work called Influence of Geometric Factors and Process-Induced Attributes of Monotonic and Fatigue Behavior of Lattice Structures, so impact of scales, unit cell size, and wall thickness. And this work was done at the final stage of my PhD together with my PhD supervisor, Professor Nima Razavi. So first, a little bit introduction about myself. Period of joining as assistant professor, I was doing PhD at Norwegian University of Science and Technology, and before that, I finished my bachelor and master in the United States. So this talk will consist 4 parts. First, I will go through a bit background and motivations, and then followed by the materials and methods. And then I will have the results and the discussions, and finally with the conclusions. So first, let's talk a little bit about the background and the motivation of this work. So as we all know, additive manufacturing, this technology has been used in the numerous fields. So from the small to the large scale, such as biomedical implants, automotive components, and constructions. It has a lot of advantages. For example, the freedom of the design, the waste minimization, and has the ability to fabricate complex structures such as the metal materials. And it has the ability for the fast prototyping. But in the same time, it has a lot of drawbacks. For example, the surface roughness will significantly impact the fatigue properties, and as also the geometric deviations. So which means the actual prototype is different from what you ask for, and also the internal porosities. So these are all the drawbacks. A little background about the lattice structures. So in general, it can be classified into 3 categories. So first is the Borrego lattice. So it has application for the football wear and also the muscle tissue modeling. And second is the most commonly used surface-based lattice. So it has the solid TPM surface and also the sheet TPMS-based surface. And normally it can be used for the heat exchanger and also for the lightweight structural components, as well as the energy absorptions. And the last would be the strut-based lattice. So it has the application for the bone struts in the biomedical implants and also for some robotic arms for the lightweighting purpose. So what is the goal for this research? So the goal is to investigate the scales, the wall thickness, and also the unit cell size effect on the mechanical properties for the uniform lattices under quasi-static and fatigue loading conditions. So why this is important? Because various scales of the lattices have great applications as I speak about the small scales to large scales. And also different scales of the lattices corresponding to different geometrical deviations, which can influence the mechanical properties such as the fatigue and also the static properties a lot. And also there is a research gap for the metallic lattices, especially for the fatigue aspect. So that makes this work important. Then let's talk about materials and methods. So in this work, all the lattices were fabricated via the aluminum silicon magnesium powders with the laser powder bed fusion methods, and also with the optimized process parameters. So 3 classifications were made for this purpose. So first is the scale effect. So which means, as you can see from the figures here, all the lattices has the constant relative densities, but increasing the scales. Okay, if we break down the scale effect into 2 different categories. So first one would be the unit cell size effect, which means all 3 lattices has the same constant wall thickness, but different unit cell size. And also the wall thickness effect, which means all 3 lattices has the constant unit cell size, but different wall thickness. So basically it has a very comprehensive studies for all the lattices in terms of the geometrical factors. So the naming rules. So in order to make the rules naming so easier to memorize, so we classified the G, X, Y. So G stands for gyroid, which is the lattice studying here. And X stands for the unit cell size, and Y stands for the wall thickness. So Once we see the name of the lattice, we can easily know what is the unit cell size and wall thickness, or the parameters of the lattice structures here. And in more details, three effects such as scale effect, unit cell size effect, and also the wall thickness effect were studied in here. So as we can see, for the scale effect, all the relative densities are the same. So please keep in mind that the relative density here are the design relative density, which means that this number was calculated based on the model in the CAD file. And also for the unit cell size effect, the wall thickness is a constant. For the wall thickness effect, the unit cell size and also the lattice size were the same. And as we know, there are three comparisons for this work. And for the lattices, which is highlighted in the middle, those lattices were used as a comparison reason. So it was repeated for 3 times. So let's talk about the results and discussion. So first, we had some analysis about the geometrical accuracy and deviations. For example, these lattices, as we can see from the figure here, the green part stands for normally there are almost no deviations. And the red parts and also the blue part stands for the deviations. As we can see from the image here, most of the deviations occur in the overhang area of the lattice structures, which is understandable because due to the fabrication, the orientation, and also the geometries. So those areas, normally they have the either lacking of the materials or the excessive powders. And if we take a deeper look into the different categories, we can see that for the first category, which is scale effect, for the percentage of the deviation, actually all the categories as a scale effect, unit cell size effect, wall thickness effect, they all have the decreasing effect, okay? And also, if we calculate the actual surface area to the volume ratio, we can see that for the first category and the third category, they are all decreasing, but the second category is slightly increasing, which is opposite trend as the percentage of the deviation. So which means for the second category, for the unit cell effect, there are other dominant factors which are influencing the trend. So enough about the geometrical deviation. So if we take a look at the internal porosity analysis, we can see that depending on the geometry of the lattices, different porosities were measured here. So for example, for the smallest lattices, we can see that there are a lot of porosities for the lattices. And as the image shows on the left, the red dots indicate the pores. And if we take a deeper layer by layer analysis for the porosity, we can see that actually the designed surface area or the cross-sectional area compared to the actual cross-sectional area, there's a huge deviations in this case. So if we take a look at the figures on the right bottom side, we can see that for the design area, there's a smooth and very nice waves. But for the CT scan area, which we can see that the area is actually much bigger, and also there is a pores inside that. So which means also during the fabrications, there is a poor qualities in terms of these small lattice structures. Quasi-static compression was also done for all these 7 geometries. As we can see from the figure on the left, the area which are highlighted in red shows the shear bend. Also, for the different scales and unit cell size and wall thickness, the figures on the right, we can see that for the stiffness and the yield strength, the comparisons, for example, for the scale effect, there is a huge difference between the design stiffness and the actual stiffness, which means the geometrical deviation is huge. But once the scale is larger, then the difference decreases. And photography analysis were also conducted. So due to the time limitation, I will also only talk about the wall thickness effect here. So basically for the fatigue loading conditions, the ratio is 0.1 with the frequency of 20 Hertz. And once the lattices reaches around 80% of the original height, the test stops, and the around 2 million cycles were defined as run-out cycles. So as we can see from the image here, the surface on the top right of the overhang areas are much smoother compared to the bottom side because of the fabrication orientations. And also for the areas with the rough surface, normally they have these excessive powders left. And also cracks initiated from the rough surface and also propagated through the thickness. And as we can see also from the image, most of the fracture accumulates closer to the center of the fracture, and also specimens with smaller wall thickness, for example, in this case, 0.2 millimeters, tends to have a few cracks compared to the specimens with larger wall thickness. And if we compare the wall thickness effect in terms of the fatigue strength, we can see that for the design relative density, the fatigue strength stayed almost the same. But once we calculate normalized with the actual relative density, we can see that from the wall thickness of 0.2 millimeters to the wall thickness of 1.05 millimeters, the fatigue strength increased actually around 63% of that. So which means the fatigue strength is higher when the wall thickness increase. And if we make a further comparisons, we can see that the fatigue limit also decrease when the scale increases due to the decrease of the relative density. And also the fatigue failure is very highly sensitive to the local deformation, which it leads to the shear bend. And fatigue limit also decrease when the unit cell size increase. So there is a lot of factors affecting the fatigue limit. And we also have the plot of the stiffness versus percentage of cycle to failure. As we can see, most of the lattices can be classified into the three categories. The first stage, the stiffness drop sharply with the increase of the percentage. And then the second stage with the much steady trend. And the third with the stiffness drop again. And also this relations is closely related to the deformation behavior. Either it's the homogeneous or the non-homogeneous materials. So conclusion. So here we can observe that the opposing relations between the manufacturing accuracy and the scale. So from the 10 to 90%. And also relative density plays an important role in this case, while the geometric inaccuracy is both raised with the actual relative density and the surface roughness. And for the quasi-static deformation, the monotonic behavior shifted from the stretching dominated and bending dominated. And the strong correlation between the fatigue performance and the scale reaches around 220%. And a little advertisement from the university. So this is the university I'm working right now, Xi'an Liverpool University. It's actually located in Suzhou, so it's very close to Shanghai. And once you visit, I'm sure you will be fascinated by the designs of the buildings. And we also have advanced labs of the additive manufacturing lab, also the advanced material characterization lab, as well as the robotics labs. So if you ever visit Shanghai, so you can reach out to me with the emails, and I will show you around. Thank you very much for your attention.